Cooking is not just about taste. Texture is also very important. But what makes sugar crunchy and butter smooth? Or coconut oil solid at room temperature and avocado oil liquid? It's all about the strength of interactions between the molecules. This is Real Chem. When we compress a material, or stretch it, or bite into it, what we experience is primarily related to the forces between the molecules, the intermolecular forces. The molecules themselves, with their strong intramolecular covalent bonds holding the atoms together, they're not affected much by our feeble poking and prodding. So to understand properties like compressibility and texture, we want to consider the types and relative strengths of interactions between molecules. Let's explore. For neutral molecules, the interactions between molecules fall into two broad categories: polar forces and dispersion forces. Let's start by considering the polar forces in hydrogen chloride, HCl. Because chlorine is more electronegative than hydrogen, chlorine gets more than its equal share of the shared electrons in the covalent bond. This gives chlorine a partial negative charge and hydrogen a partial positive charge. These partial charges lead to a dipole moment that is responsible for the polar forces. When aligned like this, electrostatic attraction between the positive and negative charges makes it hard to pull the molecules apart. Sugar is hard and crunchy because when you bite down on a sugar cube, you are overcoming and rearranging strong polar interactions. The molecules in butter and oils, on the other hand, have small dipole moments, so their interactions are dominated by dispersion forces. Dispersion forces are present among all molecules, including polar molecules, but for nonpolar molecules, they are the only force present. To see how these arise, let's consider the chlorine molecule, Cl2. The chlorine atoms have the same electronegativity, so electrons are shared equally. There are no permanent partial charges and no permanent dipole moment. But notice I slipped the word permanent in there. This is because the electrons can temporarily fluctuate, favoring one chlorine over the other. This leads to temporary partial charges and a fleeting dipole moment that points to the left at one moment and then to the right at the next. There is no reason for an isolated molecule to develop such a fluctuating dipole moment. Molecules are chill by nature. They tend not to do things that don't lower their energy. But when two molecules come together, they can collude to lower their energy. They do this by developing fluctuating dipole moments that are synchronized to maintain an attractive arrangement. It's like committed romantic partners making small compromises to enhance their mutual attraction. The more electrons a molecule has, the easier it is for it to develop these fluctuating dipole moments. So dispersion forces increase as the molecules get bigger. For large molecules, the effects of dispersion forces can rival those from polar forces. But in butter and oils, the dispersion forces are relatively weak. It's easy to break and rearrange these forces, and this gives them their distinctive smooth textures. Just like the principles that make sugar crunchy and butter smooth, the properties of many materials are controlled by their intermolecular forces. This might not be at the front of your mind when you're whipping up something in the kitchen, but for chemists designing plastics, the strength of the intermolecular interactions is one of the key factors they try to control. Weak interactions lead to soft, pliable materials. Strong lead to rigid, stiff materials. It's engineering at the atomic scale. Bet you didn't know that when you're making breakfast, you're actually also engineering at the atomic scale. So explore, and remember to have fun.